Thank you very much. So good morning, everyone, again. And it's a pleasure to be here today and to talk about something that I really enjoy talking about, recently at least. This is blockchains. Now, let me start by asking you, and may I ask you for your hands, who would say is familiar with blockchain technology? Okay, that's about a quarter of the audience. So I hope I can give you an explanation on what blockchains are. This is an attempt, and I try to do this slightly different than probably some of the other perspectives that are around on blockchains. We have April 2017. It's impossible not to notice all the hype and the discussion going on around blockchains. And so let me introduce a bit, why is there such an interest in blockchain? Is this actually justified? And given that we are a cloud research and services research community, let me take a perspective on what we've studied so far over the past decades and years, which is transaction processing from a database and distributed systems perspective, including the cloud perspective, and how blockchains will then actually relate to that. Okay? All right, so a study by IBM end of last year among 200 banks or so basically concluded that around 15% of those banks are already on their way to fully offering commercial blockchain products in the course of 2017 of this year. And I alluded to this in the panel earlier, the adoption rate of blockchain technology, and we'll clarify in a minute what blockchain technology is much, much faster than what we've seen in the past with other technologies like the cloud computing, for example. Also interesting, again, in the financial sector, is a recent study by Accenture published earlier this year, basically states that blockchain could save investment banks, the global investment banks are really meant here, with up to 12 billion a year in infrastructure costs. So blockchain, as we'll hear in a minute, is really a tamper-proof, permanent, immutable record of data. Given that you have such a record, such a immutable record, that obviously, in particular in the financial industry, changes the game completely for auditing processes, for finance reporting, and so forth. And with that, enormous cost savings are being associated along those lines. Nevertheless, it's not related or it's not restricted to the finance industry. In fact, blockchain is a technology that has gained interest across a number of industry verticals. And it applies really to any application where there's some form of trade going on and where some form of tracking of some digital asset is really of interest. And of course, in some cases, it may be actually a physical good, a physical asset, and we didn't need a digital corresponding part to it, but the opportunities are immense. And so current experiments basically range from anything, digital rights to micropayments to e-identity, all aspects of supply chain. Whenever there's information needed about the provenance of some good, of some digital assets, this is what blockchain is about and why this is so promising. Also interesting to see the investments that have taken place in the blockchain startup market. And this is not just related to Bitcoin. So blockchain was originally introduced in 2008 as a technology behind Bitcoin, but it's of course not restricted to Bitcoin or even to cryptocurrencies. Over the past 2 years, over $1 billion of US dollars have been invested in startups. So each year in 2015, 2016, the investment were over 500 million just in startup technology. And if you look at the broad range of what's going on, even for us, for example, in the cloud community, we have offerings that tend to look at cloud storage in a new way, let's say at decentralized cloud storage. But we have, of course, solutions popping up in IoT space, in the classical enterprise domain, in addition to the application-specific solutions like in the finance or in other industry verticals. So the potential for blockchain is very real. This is not just something that people are writing about, even though, of course, there's probably a lot of discussion and potentially even hype around this. But correspondingly, it's not trivial to actually implement blockchains. And even though the speed of how blockchain technology is developing and as a number of also experiences are growing with blockchain technology, there's still a number of open issues. And hopefully I can contribute a little bit to this by giving you a viewpoint on blockchain by taking a transaction processing perspective. So about a quarter of you said you know what blockchains are. And the next question I will have actually is, who are you in fact? Because depending on who you talk to, there will be different definitions of blockchain coming up. So one is what typically a business executive or an application developer perspective would be about, which says a blockchain is really a shared decentralized ledger with the purposes of business disintermediation, so remove the middleman, remove the central unit, and thereby introducing trustless interactions or trustless architectures, and thereby lowering transaction costs, okay? So trustless is a term that is, relates in the same spirit to when we say in computing something is serverless. Serverless doesn't mean there's no server, but it just means we don't care and need to manage the servers anymore like we do in cloud computing nowadays. So like here, trust is nothing we want to explicitly and expensively manage, but we'll build it in basically in a key architecture, in a key paradigm. That's the main idea behind here. By removing the middleman, be it a finance transaction or be it a peer-to-peer trade of energy or anything else like, that's a huge promise from a business perspective. Now, if you ask an IT architect and a database guy or distributed systems guy, it would slightly change, possibly. And the definition could be, it's a shared append-only database, a distributed database, with a full replication and cryptographic transaction permissioning model. Right? So the language gets more technical at this point, and you see, okay, it's an append-only database. We have full replication, and we draw quite a bit on knowledge of what replication has been in distributed systems and in cloud computing. And we introduce some cryptographic elements and protocols as well. And again, we have a transaction notion here, a different transaction notion than for the first definition, and it gets more technical then. And even yet, a third definition would be if you go to the actual blockchain developer and technology community, and they would probably say it's a peer-to-peer protocol for trustless execution and recording of transactions, secured by asymmetric cryptography in a consistent and immutable chain of blocks. All of these three views are identical, but all of these put a different emphasis. The first one obviously looks at what the opportunities are in the business space. The second takes more an architecture perspective, and the third one gets even more technical. And correspondingly, if you talk to any of these communities, you will see such a different focus. And there's even more communities. If you go to a security guy will bring in a different element. If you talk to an economics community, again, the notion will change. The definition that I would like to put up for us here in the cloud research community is it's a shared database system where no single party can modify any record without the consensus of all network participants, and in doing so, enables decentralized control and immutability of transactions. Now, these are quite some powerful words in here, because the technology, what blockchain claims to be able to do, is not something that typically is easily achievable with alternatives. All right? So a shared database system, okay, agreed. We're familiar with that. Consensus protocols, we studied them for a long time, also fair enough. Decentralization of control makes it already quite different. That's not trivial. And immutability of transactions, thinking of all the discussions around data privacy or any data record and potential attacks that may exist to such records. This is quite an interesting claim, or quite a strong claim that blockchains promote. So probably we need a bit to digest this, because it's quite a bit of a claim, because if this were true, that justifies what I tried to motivate in the beginning, why from the larger global investment banks to the smaller startup market, basically, numerous parties are incredibly interested in blockchain technology. So we've seen in definitions, in all definitions, the notion of a transaction pops up. So what exactly is a transaction? And my suggestion is, let's take a transaction processing perspective. Let's look from a transaction and TP perspective on blockchains. And I'll be talking to you mostly from now on as a computer scientist and as an IT architect. And the message I'm going to give to you, it's all about SALT. Okay? And we're going to decipher what the acronym SALT actually stands for. First of all, what are transactions as we know them? And Most generally, in common language, it's an exchange of transfer of goods, services, or funds, or it's actually the act, process, or instance of transacting. So whenever I'm giving something to somebody else, or the two of you are doing this, or even more of us, that's what we typically refer to as a transaction in the English language. In computer science, we have a slightly more restricted definition. And typically in computer science, we refer to a transaction as a logical unit of work that is being performed within some information system that we refer to as a transaction processing system, and for which we can give a set of guarantees. So that logical unit of work is typically given some guarantees on properties by the system that manages it, right? So in the 1980s, early 90s, basically, with the emergence of relational database systems, and most of us probably were not computer scientists by then, Jim Gray postulated the term ACID transaction. I believe that everyone is familiar with the term ACID transaction. You probably can't avoid this in hearing this either when you're studying computer science or whenever you hear about this, looking at relational database transaction. And it's a term still very important today. And ACID stands for atomicity, consistency, isolation, and durability. And these properties that are typically described in here, they are not necessarily trivial to be ensured. So atomicity, in a given transaction, like a funds transfer, we have a withdrawal and a deposit, we'd like to couple these and either execute both or none of them. Sounds easy, but it's not necessarily trivial to do so. Consistency refers to maintaining the referential integrity of the database, that only valid data can actually be written in the database. Assuming the initial state is consistent, every transaction would lead to another initial consistent state. And isolation, can we treat a number of concurrent transactions as if they were executed serialized, so in isolation? And given that we have successfully committed data, that data should never be lost. These are ACID transactions, and of course we could go deeper here and discuss what ACID transactions are really about. What happened around 2000 and is the term base systems and base. And the term base was, I think, initially introduced by Eric Brewer to deliberately describe something that is diametrically opposite to acid, and that's why you have acid and base, okay? Slight analogy to chemistry here, or lemons and baking soda. And base stands for basically available, soft state, and eventually consistent. And again, to us as a cloud community, I assume you're probably mostly also familiar with the base notion. Basically available means that partial system failures are okay. Soft state means that the system state can change even if no further updates are happening. Eventual consistent refers to the system becomes consistent if no new updates are being made. So all of these are, again, just like with ACID, worthwhile to study in more depth. But this is what typically cloud storage systems are mostly characterized by. Any NoSQL system is typically not an ACID system, but is a base system and refers to the base properties. And this is heavily drawn, of course, by the notion of replication and how to ensure and set high availability as a primary objective in the base world, as opposed to putting the emphasis on consistency in the ACID world. So as you can see, within base, things have been quite compromised in a way. The other interesting thing to notice, though, is that with ACID, we're referring to properties of a transaction, whereas base really refers to properties of a system. There's not really a notion of a base transaction, but any logical unit of work that would be processed within a base context could be considered a transaction. And let's try to be a bit precise here, though, because by trying to explain what blockchains are, we'll need that dual perspective. And another way to look at ACID versus base is that if you recall the CAP theorem, that you can only have 2 out of 3 properties, consistency, availability, and tolerance to network partitioning, then ACID, the ACID world, the lemon world, is really drop availability, but ensure consistency in a partitioned environment. And this is like the wedding. Right? So this is typically assured by a client talking to a coordinator and a coordinator running a two-phase commit protocol, just like in marriage, asking in two phases first, do you like to get married? Do you like to get married? If you say yes, then yes you are in the second phase, okay? Whereas in the base phase, the emphasis is really drop consistency, but focus on availability. And here, we don't ensure the consistency, we don't have a coordinator anymore, but it's really just do the update with one node. We have some responsibilities distributed across the nodes, and then ensure that the nodes talk to each other by basically promoting and propagating the respective updates. And we'll have a look shortly what blockchains are then. So if you look at transaction processing then from ACID and a base perspective, this is basically an illustration of a technical picture of a TP system in support of ACID transactions. It's a bit simplified, and in computer science we have plenty of standards included or protocols that relate to such TP systems. For example, the XOpen distributed transaction processing standard that defined also the XA interface is decades old. The same idea from the previous picture. We have a particular coordinator element, which is called a transaction manager. Any application that is interested to do an ACID transaction would need to talk to such an element. That element drives protocols, completion protocols to resource managers that talk to the actual interfaces, and the client in number 2 interacts with these, but any transaction is typically under explicit demarcation. Okay? I'm showing you this picture to contrast and explain what blockchains will be. If you look at base systems, we don't have the transaction manager component anymore. Just like as in the previous picture, no coordinator exists. In this case, the application talks directly to the resources, typically through some form of load balancing, and then the resource managers will need to talk to each other in order to synchronize. So if there's an update done to this data record and a copy is being held at this version, then they need to synchronize eventually over time and independent of the application, right? All right, so let's look at blockchains now. Are blockchains ACID or are blockchains base? And the answer is actually they're neither. And this is why even though ACID transactions are very established and so are base with NoSQL stores, the term I'd like to coin here is that blockchains are salt. So thinking a bit about our old chemistry days, it's also a contrived acronym where you take an acid, you take a base, and the result is actually a salt plus water. So this is a bit of a contrived acronym, but SALT stands for sequential, agreed, ledgered, and tamper resistant. Okay? And also we probably need a bit to digest what these terms mean. But the idea is that transactions are being processed in a sequential order. We refer to this as community consensus that determines whether a transaction is valid or not. So there's actually an agreement protocol in here. And everything that is validated, all agreed on transactions, then are consistently stored, permanently stored. So this is why we call it a ledger property. And the transaction cannot be easily, and the data records cannot easily be manipulated with, simply because we use a set of crypto protocols and other mechanisms that ensures that whatever data is being written is tamper resistant. So the emphasis, as opposed to ACID and to base, is really on these properties. And whether these properties are relevant to your application or to what extent you can actually benefit and derive value out of these, that's the exercise when engineering blockchains. Now, there's a perspective, the dual perspective here, also that relates more to the system side. So understanding transactions conceptually is one side of the medal, and understanding the systems that would support the transactions is the other side of the medal. So we use the same acronym SALT, and we basically have a slightly different version here, in that from a systems perspective, we say SALT stands for symmetric, admin-free, ledgered, and time-consensual. The background of why we're doing this is simply because ACID transactions are also more properties of the transaction, and base systems are properties of the systems. So we can easily also then, or better compare in what relationship blockchains are actually towards acid and base. Symmetric is very close to what we have in base systems in NoSQL stores that use a replication architecture. The idea is that we have a peer-to-peer network where each node has similar or shared responsibilities. The difference is we don't have any admin. In some replication architectures may also be the case that there's no admin, but being admin-free is quite a strong element, right? This is exactly what we discussed in the panel. There's no central coordinating agent anymore. Everything is being decentralized. Still ledgered, and is a similar but different version of the ledger in transaction. Everybody maintains a copy of the database. This is quite important in a blockchain context. And time consensual, we can give some guarantees in terms of how the transaction, which is a block in the blockchain world, is a set of transaction, of validated transaction, is actually being executed, right? Taking all of this together, we have a quite new concept here with blockchains. The key idea is, and we've talked about trust earlier this morning, is there's no need to trust anyone. The main idea is trust yourself and only yourself, and then assume the system consists of people like you. So if everybody just trusts yourself and agrees on these protocols, that's the idea of a blockchain. So no centralized agency, no centralized control, no third party trying to say we have a higher right or we have some legislation to actually govern trust. All of this disappears through these properties. And while it's easily and to some extent, at least I think it's nice to describe blockchains from this perspective, this would be the systems picture to that, the corresponding systems picture. And you can see it is quite different. This doesn't look necessarily like the asset diagram. It doesn't look like the base system. It comes with a bit of different sets of components and responsibilities. So we have an application that talks to a number of peers, or ideally can talk to any one of all of the peers. Typically, this is the data that I'm managing. I have some sort of an equivalence to a resource manager and some sort of an equivalence to a transaction manager, and different interfaces and responsibilities. I can create a transaction, start a transaction. Transactions are then basically validated. Everybody has, however, the right to validate, so transactions are propagated to other nodes, which in turn also validate the transaction. And only if there's different ways for consensus algorithms or consensus to be achieved, proof of work, proof of stake, there's different mechanisms here. If the majority actually agrees, then a transaction is being written and can become permanent. A block is really the unit or set of transactions, so that the unit of processing is not too fine granular, and can be appended to the actual resource, which is then held as a copy at each of the peers. With all of this, and there's more information on this that we could discuss, we have also written a short paper that should be part of the proceedings, where you can read up on some of this in terms of the processes that are going on. The immediate thing to notice, though, is this is not ACID, and this is not base, but we keep talking about transactions. And we look at application context nowadays, be it in the financial services domain or in other domains, when we say, well, let's do a blockchain-based transaction. It requires to us a change in mindset. It requires us to look different, both conceptually at what a transaction is, as well as at the systems that are in support of such transactions. If we try to compare a bit the world of ACID, so traditional relational database systems transaction, and the world of base, all of this is our NoSQL cloud storage well-known world. Then we have our salt environment in the middle, which are the blockchains, and you can already see where blockchains actually draw from the history of relational database management transactions, as well as from all the experience we have from cloud storage and NoSQL systems. We'll defer the atomicity for a moment. And yes, you can already see everything, every letter that's in red in here doesn't really have a direct corresponding part, whereas everything that is written in black has to some extent some relationship to another property in a different system. So the consistency property in asset transaction has some relationship to the agreed property in blockchain world. The isolation property does relate to the sequential property. The durability relates to ledger. This ledger is a bit weaker than this durability, has to do with over time things actually could change, but in principle they relate. Same over here for the base cloud world. Basically available relates to both the symmetric and ledgered aspect that we have in the salt world, and the eventual consistency notion does also to some extent relate to the ledgered world. It's important to say though that base properties are actually not really any guarantees, because it's relaxed in every matter. We don't say high available, so we say basically available. We say soft state, we don't say consistent, we say eventually consistent. So all of these are not really strong guarantees, whereas with here we describe actual properties, and on the left side to the asset, actual strong guarantees that are not trivial to support. Tamper-proof, time-consensual, admin-free, these are very specific properties to Salt that don't have a direct corresponding element, and this is also what makes Salt systems different, in addition to being in relationship and drawing from history both in the relational database world and the NoSQL world. Now, what about the A, though? So the idea that we have transactions that group a set of operations and where we can ensure that an all or nothing property through that element. Maybe the T in Salt could also stand for Turing complete, right? Because the A, this is the A from our asset, could be addressed by looking at stored procedures. Stored procedures, as we know them from the relational database world, and by that we don't have just data in our blockchain, but we also have executable programs in the blockchain. However, in order for the blockchain to become of the nature that we just described, all of these stored procedures, they will have to be deterministic. If they were not deterministic, we can no longer ensure the properties of a database. So we can't use stored procedures, but really have to go towards deterministic computation. And then there's essentially two ways to address this, and one is what Bitcoin is doing by simply having a reduced language instruction set on how to express those procedures so that all computations will be deterministic. And the other one is what the Ethereum world is doing. Ethereum is a different blockchain other than Bitcoin, by introducing a cost model. By introducing a particular cost model for a Turing-complete language, you can ensure also that sooner or later, basically, the computations are deterministic. Otherwise, they would become too expensive, and from an economic reason, nobody would do them. And this is really what smart contracts are, right? So even though we hear about the notion of smart contracts, there's a very specific smart contract notion and definition that comes out of the Ethereum world. This is not as smart as used in intuitively in different contexts. So this is quite fascinating when we say that, okay, our shared append-only database does not just contain data, but it also contains executable code. So why then blockchain and not transaction chain if transactions are really the unit? So a transaction is what every peer in the network can contribute to the system. A block is really a group of validated transactions, and the blockchain is then an ordered set of blocks. A block also contains a number of different other information, all of that, again, for the purposes we described earlier, typically in any of the SALT properties. So I hope I've given you some introduction into blockchains, which is different than, let's say, reading a white paper that just claims how brilliant blockchains are, or this is a perspective we've taken on blockchains from a distributed systems and a database perspective, because I believe this is, for a community like this, the most appropriate perspective. Now, how do we build systems that use blockchains? And how do we engineer blockchain-based applications? And I picked a couple of examples which are deliberately not from the finance industry to show you basically just exemplary, a couple of startups that do something different. And Monograph is a startup. We have no relationship to them, by the way. It's just interesting to observe what is going on. That address artists, be it either in the music industry or in the fine arts context, who have digital art and like to actually bring them on the market and sell them, and have, of course, both the rights management be managed as well as the actual trade be supported, without any larger corporation that would govern such a trade. It's an interesting case where you can see that Monograph can benefit from blockchain technology. This is happening in the real world. To describe this a bit, we just use sort of simplistic, simplified process diagrams here. But the idea is that an artist or a media creator would create artwork, would then register the artwork and list it in a catalog. The media owner basically has a number of activities, and in the middle is what we're interested in this particular context here, is the data management. And you can see that in the case of Monograph, they actually use two different blockchains. They use a Bitcoin-based blockchain for payments, and they use an Ethereum-based blockchain for owner history, who actually owns the digital artwork that is being subject of interest here. And they also use Couchbase and AWS S3, to say conventional NoSQL stores, for the art portfolio and the sales contract. So quite an interesting use case where we see that the data management uses different data management technologies, including established traditional cloud technologies, in combination with blockchain technologies, and even two different blockchains in this case. And again, it's worthwhile to look sometimes into some of the applications and how they really be done. A second example I'd like to tell you is a company called Provenance. And in this case, we actually do work a bit with Provenance together. Provenance is a company that tries to tell you the provenance, the way your food that you're consuming, that you're finding in a supermarket or that you're eating, where it actually comes from, right? So they had an interesting case study a couple of years ago, basically looking at yellowfin tuna that is being caught in Indonesia. And basically from the moment the tuna fish is being caught, the fisherman writes a digital record into the blockchain. In real, it's actually not into the blockchain, but into another system that would then be mapped into the blockchain. And the entire way from Indonesia, from the fisherman to the actual location of where you can purchase or consume your tuna would be traceable. Again, with the idea of having an immutable data record. Nobody can manipulate and tell you that something was broken in between. And there was no central agency that you needed to trust, and somebody just told you, well, this is safe, this is fair trade. No, this is not happening. It's a completely peer-to-peer system. Now, if we look again then at provenance, we can also try to draw a picture like this, and we see we have a fisherman here, we have a supplier, we have a factory, we have the point of sale, and again, we have data management in here. And you see different activities starting from registering a catch to tagging and shipping and scanning and different activities. Of course, again, it's a simplified picture, but it's to illustrate again, how does the data management look like with provenance? They use a blockchain by Ethereum, Ethereum-based blockchain, and then they have a traditional, more or less traditional ERP system, and a traditional relational database management system, okay? And again here, the data management is not exclusively blockchain. It's also not exclusively asset transaction or exclusively base. It's again a combination of this. So, and there's more interesting cases, and I deliberately chose two which are not in the finance industry, but of course in the finance industry we see probably have the most maturity in the uses of blockchains. Now, if we take these three pictures, this was the asset diagram, this was the base diagram, this was the salt diagram, and we've just seen that typically a combination of these is in place. and people will be using, or applications, require a bit of everything. And we said this is acid, and we have particular properties associated to acid. On the other side, this is base. It's a highly available system that scales to modern web demands, to the highest web demands. In the middle, we have salt, where we say we have trustless interactions, that basically come with a set of properties. What if we take these together? What's the overall property actually of the system? Will a combination of these still be salty, or will it be just bad taste? Or is it well seasoned, so to say? This is subject to exploration, and I would like to invite you as a cloud and research community also to look into aspects like this. So what are the actual properties of blockchain-based systems? We are at an early stage in understanding how to engineer with blockchains. So the key points to take away is blockchains are very real. This is not just a hype that popular magazines and bloggers write about. It's actually really happening. A lot of investments are taking place. And I'd like to suggest to you to think of blockchains as being solved. So they are sequential, agreed, ledgered, and tamper-proof from a transaction perspective, and they're symmetric, admin-free, ledgered, and time-consensual from a systems perspective. Blockchains, transactions, and blockchain systems are an alternative to ACID transaction-based systems. They have a different TP architecture, and they have different consequences on the application architecture. Right? And I've briefly sketched that many applications will actually use a combination of ACID, base, and salt, but the overall properties of such systems are yet to be explored, and what we can ensure, what we cannot ensure. So I hope I did raise your interest into blockchain technology, and let me do a bit of advertisement to the end. I'll be very brief. So if you're curious, if you're passionate, and if you have a research and engineering mindset, I would like to invite you to collaborate. We will even be hiring very soon. You probably all have excellent jobs, but maybe not, or maybe you know somebody, or maybe you're interested to explore more. We've been just granted a project by the Economics Ministry where we're going to look at, so to say, a blockchain blueprint for photovoltaic energy systems. The idea is that individual homes who have a photovoltaic system on top of their roof, for example, they're no longer just consumers of energies, they're also producers. And in a setting like this, a decentralized architecture is the key, where direct trade among either those parties or even other energy providers will take place, and this is where we want to explore blockchain technology. And another activity starting is we're in Berlin, of course, one of the hubs in Europe for any IT startups. We'll be starting a blockchain incubator. Again, the notion is IPOs are history. Of course, it's still taking place. But what's happening in a blockchain world are ICOs, initial coin offerings. Completely new ways to think of organizations and how to start your own company for whatever purposes you're going to be addressing. We're planning to build a crowdfunding platform for blockchain-based solutions, looking at also extending the outreach to community, and possibly in doing this also with you. So happy to discuss both with you. With that, I'd like to thank you for your attention and happy to take any questions.